Hi everyone to today's GOCC. Before we start, before I introduce the speaker, I want to remind all of us of the community statement with the 3 guiding principles. We are all learning, everyone has something to contribute, and no one has all the answers. With that said, it's my pleasure to introduce to you Katie Brugge. She's not only our today's speaker, but she's also one of our new organizers. So please welcome everyone, Katie, and she will be talking about counting facets of symmetric edge polytopes. The stage is yours.
All right, thank you. Thank you everybody for being here today. I'm so excited to be talking about this. For a couple of you, this is the unabridged version of a talk that I gave at an AMS sectional this weekend. So if you are hearing this for the second time, thanks, welcome. I'm so glad you guys are here. So as we said, I'm talking about facets of symmetric edge polytopes. So a good place to start with that would be the definition of a polytope. So in general, a convex polytope is a convex subset of a real space R to the D that can either be described as the convex hull of finitely many points in R to the D, or as the bounded intersection of finitely many half spaces. Every polytope has a description both by its vertices, so as a convex hull, and by its bounding hyperplanes, called the V description and the H description, respectively. And furthermore, where we set, we say that a polytope is a lattice polytope if the points that it is the convex hull of are integer points. So we could call it a lattice polytope or an integer polytope. So the type of polytope I'd like to talk to you about today is a symmetric edge polytope, which is a family of lattice polytopes that are defined using the information of a graph. There are several ways to define polytopes from graphs. This is just one of them. So given a simple graph G with vertex set V and edge set E, the symmetric edge polytope is a lattice polytope that lives in the real space where the coordinates are indexed by the vertices of the graph. And we get the points that we're taking the convex hull of by saying that for every edge in the graph, we take the point that is the difference of the unit vectors associated to that edge, and we take positive and negative of that. So as an example of this, it's kind of weird to see from just the definition. If we took the graph that is just the complete graph on 3 vertices, this polytope is going to live in R3. And we end up with this hexagon where our vertices are, here is our EU minus EV coming from this edge, and our EV minus EU coming from the same edge. Here from the edge VW, we get EV minus EW and EW minus EV, et cetera, and for completeness sake, here is our EU minus EW and EW minus EU. Okay. So a fairly straightforward way to define this polytope from the information of the graph. And these polytopes have a lot of nice properties. So they always contain the origin, right? We can see this if we take just the convex hull of any 2 opposite vertices. The origin is contained in there, so it's contained in the whole polytope. They are centrally symmetric, which means that whenever we have a point that is in the polytope, we also have its negative in the polytope. And these guys are not full dimensional. They are always codimension 1. They live in the hyperplane that is defined by the sum of all coordinates is equal to 0. So if we sum over all the vertices in the graph and take the coordinates of a point in our polytope, or sorry, if I said 1, I meant 0. The sum of all coordinates is equal to 0. Sorry about that. But by for the same reason as, let's see that, sorry, I'm very tired. Because we live in this hyperplane where the sum of all coordinates is equal to 0, this is exactly the orthogonal complement of the span of the vector of all ones. So we are orthogonal to the vector of all ones, which is going to become a useful fact for us. And final interesting thing, not final interesting thing, the final interesting thing I'll say right now is that these polytopes are reflexive, which means that their dual polytopes are also lattice polytopes, which is a very cool property that only finitely many polytopes have. So that's kind of awesome. And because of this reflexive condition, we also have that the hyperplanes that support facets in this graph, or in this polytope, have very specific structure. Any hyperplane that intersects the polytope piece of G in a facet, we would call these facet defining or facet supporting. Is of this form where X is in this hyperplane if the sum over the vertices in the graph of f of v times xv is equal to 1, where f is some function from the vertices of the graph to the integers. So we can think of these functions as integer labelings of the vertices of the graph. Okay. So we actually can have a description of which functions these are, and that was given by Higashitani, Yahemko, and Michalek in 2019. They told us which of these integer labelings actually give us facet supporting hyperplanes. So if G is a finite simple connected graph, okay, then a function f is facet defining if two conditions hold, and it's an if and only if. Okay? So for every edge in the graph, the difference of the labels that we put on the two vertices of that edge can differ by no more than 1. Okay? So the difference is less than or equal to 1. And the set of edges for which that difference is exactly 1 forms a special subgraph of G. It is a spanning connected subgraph that we will call a facet subgraph. And finally, because we are living in this space that's orthogonal to the span of the all ones vector, we say that we're going to treat two functions f and g as the same if they differ by a common constant. So what I mean by that is if we have a function f, we can identify that with f plus c for any constant c. Okay. So this is giving us a bijection between certain integer labelings of the vertices of the graph and facets of the polytope. So we now have a strategy for counting these facets. If we can find all of the appropriate integer labelings of the vertices, then we can figure out how many facets there are. But this constructing these from scratch is kind of difficult in general, right? You can't just sort of throw an integer labeling at the graph and expect it to meet the conditions, right? So we have some help from a theorem from a couple years ago that gives us more information about what these facet subgraphs have to look like.
I have a quick question.
Absolutely.
Going back to the definition where we were calling these functions equivalent if they differ by a common constant.
Yes.
Is that kind of coming geometrically from the fact that our polytope is living in more dimensions than the polytope itself has?
Exactly, yes.
Okay.
So if you think about like our two-dimensional hexagon, right? Any hyperplane that sits on a facet, we could also have a differently tilted hyperplane that still supports the same facet. And that modding out by the all ones vector is what tells us we're going to treat all of those tilting hyperplanes as the same. I
see. And the all ones vector would be adding everything to all of your labels. Okay.
Yes, exactly. Yeah, excellent question. Okay. So we have this further description of which subgraphs can be facet subgraphs. Right? So if G is a connected graph, a subgraph H is a facet subgraph of G, if and only if it is a maximal connected spanning bipartite subgraph of G, which is a lot of words. The connected and spanning condition comes directly from the theorem on the previous page. Our graphs that were facet subgraphs needed to be connected and spanning. But this maximal and bipartite comes from the restrictions we get from the functions themselves. Okay. So as an example of this, if we go back to our triangles, these are the three facet subgraphs of the complete graph on 3 vertices. So solid edges in these graphs represent edges that are in the subgraph, and dotted edges represent edges that are in the original graph but not in the subgraph. So the way that we construct our labelings from these is every solid edge has to have its endpoints having difference 1. So these have to differ by 1. And every dotted edge, its endpoints have to have the same label. So these have to differ by 0. So with this in mind, it becomes easier for us to figure out which labelings of the vertices actually become facet functions. And another thing that we can do, because we have this property of being able to mod out by the all ones vector, is that we can fix a label on a specific vertex for every single facet function. So I'm going to fix that in all of my functions, the label on the vertex u is 0. So if I do this on this first facet subgraph all the way to the left, if the label on u is 0, then the label on v has to either be plus or minus 1. If I choose it to be plus 1, then this constant edge tells me that the label on w also has to be plus 1. Okay. But I could have also made the choice, if u is still 0, I could label v with a minus 1, and w would also have to be a minus 1. Okay. And following through the others, in the middle subgraph, if u is 0, w also has to be 0, and v is plus or minus 1. Here, if u is 0, then v is also 0, and w is plus or minus 1. Okay. So these are our 6 facet functions that we saw actually coming up as facets of our hexagon from the original example. Right? So this is the game we play. We figure out what the structure of the facet subgraphs has to be. And then to count the facets, we go to each subgraph and say, well, this edge has to, if we start here, this edge either has to ascend or descend. This edge has to either ascend or descend, and this edge has to be constant. So how many ways can we make those compatible with each other? Right? So this is what we end up doing. And this strategy works out to give us some good results in some very sparse families of very sparse graphs. So before we get to those results, one other thing that we get from this is a notion about what happens when we identify 2 graphs at a single vertex. So if we're going to let n of g denote the number of facets of piece of g, then if we take the wedge product of 2 graphs, just take g and h and identify them at a single vertex, then the facets are multiplicative. So the number of facets of g wedge h is the facets of g times the facets of h. So for a few families, this kind of gives us everything we need. So if T is a tree on n vertices, we know that n of T is equal to 2 to the n minus 1, because every tree can be thought of as a wedge of n minus 1 edges with appropriate choices of identification points. And a single edge has a symmetric edge polytope with 2 facets. Okay. And for a connected graph G with n vertices and n edges, right, this is a tree where we have added one more edge somehow, n of G is completely determined by the length of the unique cycle in G. We'll write that in, length of the cycle. Okay. And this being completely determined, we can formalize a little bit in this corollary. So if C of nm is a graph with n vertices and n edges that contains an m cycle, then its number of facets is given by these products of binomial coefficients and powers of 2. So the binomial coefficients, or m times a binomial coefficient, is coming from the number of facets of the m cycle. So this is the Cm. Right? And this 2 to the n minus m is coming from the tree parts that we're wedging on. So this is not too bad of a facet count. It was fairly easy to come by with the tools we had. And with this, we were able to describe what the facet maximizing graphs are in this family. So among all connected graphs with n vertices and n edges, the number of facets is maximized by C of n, so just the n cycle when n is odd, or C of n, n-1 when n is even. So that would be an n-1 cycle with another edge attached to it. So the theme seems to be, with these graphs with n vertices and n edges, that you maximize your facets by taking the biggest odd cycle you can get. And we will see that pattern kind of continue as we move through. Okay. So this case with n vertices and n edges came fairly easily, fairly straightforward. So the next question became, how hard could it be to add one more edge? And it turns out pretty hard. So when we start to consider graphs with n vertices and n+1 edges, we need to consider a family that I came to call coffee bean graphs, and hopefully you'll see why in a second. So if we take a vector of positive integers, call it m, then CB of m is going to denote the graph of t internally disjoint paths of length m1 through mt that connect to endpoints. So we've got paths living up here, and we just connect them at their endpoints. Okay. In the literature, sometimes these will be referred to as theta graphs when all of the paths are of the same length. To maybe motivate why I would call these coffee beans, I picture them kind of like this. Right, here are the identified endpoints of our paths. And we've got a path of length 3, a path of length 2, and another path of length 2. This is CB322. Okay. And hopefully you can see why my caffeine-fueled grad student brain would want to call these coffee beans. Okay. So we can count the facets of graphs like this. And this theorem here says that if all of the entries of M are the same parity, either all even or all odd, then the number of facets of CBM is given by this function f that is a sum of products of binomial coefficients. So m of t is the length of our smallest, or sorry, m sub t is the length of our smallest path. And then we multiply by a binomial coefficient for each additional path that we've got along the way. So to kind of sketch out the proof of this with a particular example, if we look at CB422, which is given here, the idea of this proof is that when all of the paths are even length or all the paths are odd length, then this graph is bipartite. So its only facet subgraph is going to be itself. If we try to partition the vertices in a different way and make the bipartite subgraph we get from that partition, that thing will be disconnected. So the only facet subgraph of this coffee bean is itself. And so we will count the facets by counting the valid labelings of the edges as either ascending or descending. Okay. So if we start this by fixing the label on our top vertex to be a 0, and think about orienting all the edges away from that top vertex. Okay. If we start on our shortest path, we can make a choice of how many ascending and descending edges we have. So if I make the decision that this edge is going to be ascending, and this edge is, and this edge is going to be descending, then I know that the label on this vertex is going to be a 1, and the label on my other identified vertex is going to be a 0. But now that we have labeled this vertex as a 0, it has determined how many descending and ascending edges we need on this path and how many we need along this path. Right? So once the choice of ascending and descending edges is made on the shortest path, it determines how many choices we have on the other paths. So if we have chosen, for example, on our shortest path to have j descending edges on each of our other paths, so we'll make this an M3 in this case. on our middle path, we need to have, excuse me, M2 choose 1/2 M2 minus M3 plus J, descending edges. And on our longest path here, M1, we need to have M1 choose 1/2 M1 minus M3 plus J. Okay. And since we can do this for every number of descending edges that we could place along this path, we will take the sum from J equals 0 to M3 of these binomial coefficients. So we get a term like this for each of 0, 1, and 2, because we could have no descending edges, 1 descending edge, or 2 descending edges here. Once we figured out that like labeling the edges as ascending or descending was kind of the right way to think about it in this case, the proof wasn't too bad. But it still led to not the prettiest looking formula. So what do we have next here? Yes. So we can also count the facets when our coffee bean graphs are not bipartite. So in general, when we have a vector of positive integers that has some even entries and some odd entries, we get counts for the facets that look a little more gnarly. But essentially, these come from the number of ways that we can construct a facet subgraph for that coffee bean. And then how many facets do we get from each of those facet subgraphs? Okay. So in the case where all the entries of M are at least 2, every facet subgraph we can construct, we can think about it as a smaller coffee bean. So we're still counting the facets coming from those facet subgraphs with the function f. When we've got some entries, some paths that are of length 1, if we construct facet subgraphs from those, we can think of some of those as wedges of cycles. And maybe a little intuition for this coming from here. So this is a coffee bean graph that is not bipartite. So the 2 ways to construct facet subgraphs of this are to either remove an edge from each of the even paths or remove an edge from each of the odd paths. So if we remove an edge from our even path, let's use the fancy iPad functionality here. If we remove an edge from this even path, right, it becomes a dotted edge in our facet subgraph. And now the labels on the endpoints of that edge have to be the same, right, by how our facet functions are defined. So we can think of this edge as actually being contracted. So this edge contracts, and we can think of this graph as now a coffee bean with paths of length 3, 3, and 1, because our path of length 2 was contracted down, right? And the facets of this, we know how to count. They are counted by f of 3, 3, 1. Okay. And there were 2 ways to make the choice of how to cut this edge. We could have cut this one or this one, which is where that product of path lengths is coming into play. Right? Similarly, if we decide instead to cut our odd paths, right? Say we make this choice and this choice, oops. We can think of now contracting each of these edges, and we can think of this graph as a CB222 with facets counted by f of 222. So these formulas that we had on the previous page, right? These products are counting all of the ways that we can choose which edges along even paths to cut. And once we have cut those paths, those even edges on those paths, this is the number of facets we get. Similarly, how can we cut odd edges? And what do we have after we cut those edges? Yes. Okay. So this looks pretty nasty, but the intuition for it is okay. I got a question. Yes. So the question is, why does this cutting operation work and why do they combine after cutting? So we can think of this. So the cutting operation is just figuring out how we construct facet subgraphs. So if we want to find a bipartite subgraph of this graph, we're going to need to remove some edges. So we're going to remove edges from our starting graph until we get to something bipartite. And it turns out that for graphs of this structure, the only way to cut edges to get a bipartite graph that stays connected is to cut an edge from each of the odd length paths or to cut an edge from each of the even length paths. If we do any more than that, we end up with either something not maximally bipartite or not connected. Yes. So once we say that these edges that we've cut are no longer in our facet subgraph, they become dotted edges that have to be constant at their endpoints, right? This and this has to be the same by the rules of how our facet functions have been working. Okay. Awesome, thank you. All right. So with this kind of stuff in mind, make sure I didn't miss anything else. Okay. Right. We can start considering facet maximizing graphs in the family of graphs with n vertices and n+1 edges. So if we let m of n be the number of facets that we get from these particular graphs, okay? You can take a second to look at these, but I will tell you the theme here is make the two biggest odd cycles you can and wedge them together. And if there is any edges left over, excuse me, just wedge them on as well. So the idea is make the biggest odd cycles you can. And then wedge them. And we have a conjecture that these are exactly the facet maximizing graphs among the family of graphs with n vertices and n+1 edges. So we do have proof for this conjecture in some cases. So this holds for graphs with two edge disjoint cycles. Two edge disjoint cycles. The proof of that just kind of comes down to messing around with inequalities related to binomial coefficients. Because when you've got wedges of cycles, we know that their facet counts come from products of binomial coefficients. And we also know this holds for G containing a coffee bean graph where all of the path lengths are even or all of the path lengths are odd. So G containing a CBM with all the same parity. Okay. And this proof is some not very pretty looking casework that involves a Stirling bound on n factorial and some like pretty crazy looking inequalities. It's several pages long in the paper and it's not fun to read, but trust me when I say it is true. So we do know this holds for these cases. And the only cases remaining are those where our graph contains a coffee bean, but that coffee bean has mixed parity path lengths. But we do have some progress toward that case. So for n greater than or equal to 10, we have a conjectured maximizing coffee bean for every n. So if we restrict ourselves to graphs that are coffee bean shaped, for every possible n, we believe that these are our facet maximizers. This has been tested for n up through, I think, like 535 by using Sage to just go through every partition of n plus 1 and compute what these numbers have to be. And we are finding that these are the maximizers. And along with this case, so if these conjectured maximizing coffee beans actually are maximizing coffee beans, in the even case, we can prove that the number of facets of these is less than m of n. So that we know to be true. If these actually are the maximal coffee beans, then they do obey the bound we think they should. We haven't been able to prove anything similar in the odd case, but we have checked that for every n up into a couple 100,000, that the facets of these are bounded above by m of n. Okay. So this case-by-case basis of just trying to up our number of edges got fairly complicated fairly quickly. So at this point, we decided to kind of shift focus and look at different families of graphs. In particular, graphs that are generated by random graph models. So there was a lot of experimental work done for these projects. And with our randomly generated graphs, we also wanted to look at if there was any relation to other metrics that we could have on our graph or other properties. So a property of graphs that is important to some people in network science who are studying social networks is this idea of clustering coefficients. So for every vertex of a graph, we can define the local clustering coefficient of that vertex to basically be just a measure of if I'm a vertex and I have two neighbors, are those neighbors also neighbors of each other, right? And we can take the average local clustering of an entire graph by just taking the average of the clustering coefficients for each vertex. So in the book on networks that I read this in, this was called a measure of transitivity for a graph. Right. And it's not too difficult to see how people studying social networks would be interested in this, right? How likely are two of my friends to also be friends with each other? This type of thing. Okay. So we wanted to look at this metric with graphs generated by some different models. The first model we used was the Erdős-Rényi model, GNP. This is often just called the random graph model. It plays well with proving things. Basically, to construct an Erdős-Rényi graph on n vertices with probability p, you take all of your vertices and put them in a cloud and include each possible edge independently with probability p. Right? We also used some Markov chain Monte Carlo sampling methods to sample from the space of graphs with n vertices and a fixed number of edges. And we use similar techniques to sample from the space of graphs with n vertices and fixed degree sequence. Degree sequence. So those Markov chain Monte Carlo methods are basically, we think of all of the graphs in our space as vertices on some like meta graph or a graph of graphs. And there is a way to transition from one graph in our space to another graph in our space if you can perform some local operation on one graph to get to the other graph. And then to sample from this space, you take a random walk around your graph of graphs and pull your samples at fixed intervals. Okay. So we
I
wanted
have
to
a
see.
quick question, sorry.
Yeah, absolutely.
So I only know things about random graphs from bits and pieces of talks.
Mhm.
As I recall, your first method of generating random graphs and the second method of generating random graphs have some theorem that says that these things will look roughly the same for large n values. Is that true? I thought there was a relation between those two ways.
This I am not sure about.
Okay.
What I can say is that when you define your local operation appropriately for these Markov chain Monte Carlo methods, you get the distribution you expect from your samples is the uniform distribution, and the distribution for GNP is, I know it is not the norm or the uniform distribution. I forget what distribution it is.
Okay.
Yes.
Thank you.
Yeah. So we wanted to see how clustering popped up in any of these samples that we got. And so I'm going to show you some different things. These are all pretty representative plots for all of the experiments we ran. So for GNP, we wanted to plot average local clustering against number of facets. This is a sample of close to 5,000 connected graphs on 11 vertices with edge probability 0.45. And we see that there isn't really much relationship that we can see here between the local clustering and the number of facets. It's pretty spread out from clustering 0 all the way up to clustering probably close to 0.8. Let's see. You are probably right that GNP should look like a binomial distribution, but I am not sure. Yeah, so there's a question in the chat. Yeah, so we're seeing here that when we try to put average local clustering together with GNP, there's not too much that we can see. Other than that, we seem to have some concentration of graphs right around here having average local clustering about 0.45, and that is to be expected. So the average local clustering of these GNP graphs, we expect to be the same as the edge probability. Yeah. But not a ton to see here. So if we restrict our space to graphs that have a fixed number of vertices and fixed number of edges, we start to see things like this, where our range on the clustering values we see is starting to tighten in a little bit. And it seems like higher average local clustering is starting to look like it's correlated with higher numbers of facets, but that variance is kind of changing. Our like cone is getting wider as our average local clustering goes up. And if we restrict ourselves even further to graphs with a fixed degree sequence, we even see that go away. So our average local clustering has tightened even more. So this is from 0.6 to 0.76. And we're kind of seeing most of our data points kind of bounded in this thing that doesn't look like it's getting wider. So this is data from graphs on 18 vertices having this nice fun degree sequence. In our experiments looking at degree sequence, we focused on regular graphs where all the vertices have the same degree. And we also wanted to look at graphs that have hubs, which are vertices that are very highly connected while everything else has relatively fewer neighbors. Again, because we were wondering if there could be anything related to network science here, and graphs with hubs are graphs of interest in those studies. So we're seeing that this clustering is tightening up when we restrict our space to be, we restrict the structure of our graphs even further. We don't know why this is happening. It's tough to prove results about these models because they are based a lot on just experimental data. But there was something interesting that we saw with GNP that I did not mention before. So we kind of saw, so though there's not a major trend happening with clustering here, we do see that our sample seems to have this like approximate lower bound happening. And that lower bound seems to be getting less approximate as our clustering increases. And this is our same sample of graphs coming from G11.45. Okay, so these are graphs on 11 vertices, and it's seeming like we have this lower bound occurring approximately at 2 to the 11th, or more specifically, what I believe to be true is at 2 to the 11th minus 2, 2046. Okay. And we saw this, let's see what is in here. Yeah, we saw this in just about every sample we looked at, that there appears to be an approximate lower bound for the number of facets of our GNP graphs occurring at 2 to the n minus 2, which is also the number of facets that we get from the complete graph on the same number of vertices. So this was very cool to us when we first started looking at it. We hoped that it meant that these GNP graphs were sharing a lot of the same facets with the symmetric edge polytopes for Kn, and something like that turns out to be true. So we wanted to look at what are the facet subgraphs for a graph generated by GNP. And to do that, we defined these B of AG graphs. So for any bipartition of the vertices of a graph, we denote by the graph B of AG to be the induced bipartite subgraph for that bipartition. So for example, if we take this 4 cycle and we partition the vertices into C, U, and W, and V and X. With this bipartition of the vertices, right, we take one of the shores to be U and W, and we take the other shore to be V and X. Okay. And include an edge in this induced bipartite subgraph if it is an edge in the original graph that goes between the shores, right? So here, the induced bipartite subgraph, well, U is connected to X and U is connected to V, coming from these 2 edges. And similarly, W is connected to V, W is connected to X, coming from these 2 edges. So the induced bipartite subgraph for this bipartition is just the graph itself. So here, B of AG is equal to G. But if we chose a different bipartition of the vertices, for example, if we said, let's do U by itself and VWX over here, okay. U, VWX, let's try that W again. Well, U is connected to V and U is connected to X, right? But W does not have any neighbors on the other shore, so it becomes an isolated vertex. Okay. So this is just another way to look for candidates for facet subgraphs, right? These induced bipartite subgraphs of G are exactly the graphs that could be facet subgraphs if they are connected. So for GNP, we were interested in knowing if we could say anything about when is B of AG connected. Because if it is connected, then it is a facet subgraph, and we know that we're getting facet defining functions coming from that graph. So we enlisted the help of Matt Cayley at Ohio State, who does a lot of great things with probability, and got this theorem out of it. So we first note that a sequence of events, E sub n, occurs with high probability if the probability of E sub n goes to 1 as n goes to infinity. So for n sufficiently large, these events are becoming more and more certain. So we were able to establish a threshold probability for when certain partitions of the vertices give us a connected subgraph. So if our probability, kind of the important part here, is if our probability, our edge probability is greater than 1/2, then every sufficiently even bipartition of the vertices, so here's our sufficiently even condition, every sufficiently even bipartition gives us a connected spanning B of AG, which are exactly, in other words, can I put it in here? i.e. B of AG is a facet subgraph. So for n sufficiently large and for edge probability greater than 1/2, we can say with pretty much certainty that if we split up the vertices of our graph evenly-ish, we are going to get a connected spanning bipartite subgraph from that, which is going to be a facet subgraph, and we're going to get facet defining functions from it. Okay. And as a corollary of this, if we have a collection or a sequence of graphs Gn that are all coming from GNP, so this n and this n are the same, if we fix a probability greater than 1/2, then any sequence of bipartitions for those vertex sets where each one is sufficiently even, with high probability, the only facet functions that we get from those bipartitions are exactly the same facet functions that we get for the complete graph. Okay? So not only can we say that these graphs have a lot of the same facet subgraphs as the complete graph, we can also say they have a lot of the same facet hyperplanes in a certain case, which is kind of lending credibility to that pattern that we saw, where the number of facets of the complete graph seemed to be a lower bound, which was very, very cool. As kind of a final thing, something that we were further interested in was like, what else can we say about these induced bipartite subgraphs? And we ran this experiment with some 11 regular graphs on 5,000 vertices, so very, very big and very, very sparse graphs, and just sampled some bipartitions of their vertices to see how many of them gave us connected graphs. So here, each of the colors represents a different 11 regular graph on 5,000 vertices, and we sampled 5,000 bipartitions of the vertices for each of them, and found that for all of them, it seemed to stabilize that like at least 98% of the of the induced bipartite subgraphs we saw turned out to be connected and were facet subgraphs. This felt incredibly surprising for how sparse these graphs are. An 11 regular graph on 5,000 vertices, I think we computed contains like something like 0.22% of all possible edges. So the fact that we got all of these samples to have such high percentage of connected facet subgraphs seemed very crazy. It should be noted that everything about this sample is small. We only did this for 11 graphs, and let's see. Yes, and the number of bipartitions we sampled for each graph was, I believe, also 5,000, which is a very, very small fraction of the 2 to the 4,999 possible bipartitions. But it still seemed very unlikely, and I liked the colors in the picture, so I thought I would show it to you. But yeah, so this is the work that we've been doing with symmetric edge polytopes. We are not the only people working on them. There has been a lot of work in the past couple of years looking at different geometric aspects and things like this. But hopefully I give you a little taste of it today. And that's all I've got for you. So thank you.
Let's thank our speaker. Are there some questions?
Hi.
Hi.
Hi, lovely talk, Katie.
Thank you.
So in this case, we are talking about random graphs. That's why your connectedness for the subgraph has the probability stuff in it.
Yes.
So in a normal scenario, is there like an equivalent condition? So what I can see is that if you pick 2 points in an independent set, then your thing should be disconnected, right? So if they're independent, they don't have an edge, and if you just select them separately, you should not have an edge between. Is that correct?
I would imagine so, yeah.
So is there like an equivalent condition that says, so yeah, for the same problem, so instead of working on random graphs, are there results for other graphs which are like, if you have this condition, this is equivalent to saying that your subgraphs, the bipartition subgraphs will be connected, like say for on a complete graph or like a simpler.
Yeah. This I don't know. I don't know if anyone has thought about it from that angle. It would be very interesting. I know that there are people thinking about like what sorts of operations you could do on a graph and like how they would relate to counting facets or how the formulas would change. For example, like what happens to the number of facets when you have a graph and you contract an edge. I know that people are interested in that. But I'm not sure about like, I guess like obstruction conditions, maybe you could say, or like non-existent conditions.
Yeah.
That would be cool. I'd like to think about that.
Okay.
Thank you.
So I have a question.
Mhm.
So back to the non-random stuff,
Yes.
the stuff I guess typically with few edges.
Mhm.
So you've studied the number of facets. Is there anything you can say from the spanning, connected, whatever, bipartite subgraphs about the structure of those facets, the combinatorial type?
This is not something that I have studied, but I know there was a group fairly recently who wanted to look at when those facets were simplicial.
Mhm.
I just learned about that this weekend, that someone was studying that, but it was very cool. Yes, I am not sure if there has been a ton of study about the structure, like once we know how many facets there are, what do they look like? Yes, that is a topic of interest for people who study these polytopes in more applied settings. These are related to so bounding the number of solutions to differential equations that follow the Kuramoto model, that model coupled oscillators. And people are interested in knowing like the maximum volume of a facet on these polytopes, because that's related to bounds on solution sets. So there is interest in understanding facet structure in other ways, other than just counts.
Okay.
I had a question.
Mhm.
So in the random part, you were, in order to explain that lower bound, you determined whether or not the graph shared a given maximal connected subgraph with the complete graph by just doing vertex partitions.
Yes.
And so, but then you made a comment that I don't know if I quite caught about, so that's a subgraph, but then we need to label that in order to actually create the facet. And so is there an inclusion, like it feels intuitively, it feels like if I have a labeling that works for the complete graph, that should work for my other graph, which also has as a subgraph. Is that not always the case?
That should be the case.
Okay.
Yes. So the complete graph, if we think about like a facet subgraph of the complete graph,
Mhm.
so we'll put our like complete graph on 3 vertices here,
Mhm.
right? Not only do we have a condition on how we have to label the endpoints of these edges here, but
Mhm.
there's also a restriction that goes here.
Right.
But if this edge was not an edge in our original graph, if we just had
Mhm.
this path, all of those same functions that worked up here would still work here, and we get more because we don't have a restriction about those endpoints anymore.
Okay.
So a function I could put on this graph is 0, 1, -1, but that wouldn't work up here.
Okay.
Yeah.
I guess my second question is, if those are, that set of labelings are facet defining hyperplanes for so many of these polytopes, is there a full description of those particular hyperplanes?
Of the ones for the complete graph?
Of the labelings of vertex, of, I guess these would just be all of the, I guess this would just be the full description of the facet for the complete graph, because I think every maximal connected one is of this form for the complete
Yes.
graph, correct? Yeah.
Yeah, and in that same paper where they defined, sorry, I'm gonna give you a little whiplash for a second. In that same paper where they proved this theorem, Higashitani, Yahemko, and Michelik also like gave a description for what the facet functions are for the complete graph.
Okay.
You can use this description. I'm fairly certain, I would have to look back. It's just all functions from the vertices to the set 0, 1. With this like identification of differing by a common constant. That's where the -2 comes in.
Okay. That is interesting and something I would need to think about to understand why that is the case.
Okay, but we are hitting the full hour, so I guess it's time to thank our speaker again.
Thank you, everyone.
And more questions can be asked after the recording has stopped.